Next up, we have Maria Buzzo. So please take it away.
Yeah, hello, everyone. Thank you so much for having me. My name is Luisa. I am a postdoc at Yale University, soon to move to Northwestern as a Sierra Fellow. And today I'd like to talk a little bit about the luminous and dark matter content of ultra-diffuse galaxies. So I'm going to move away from streams a little bit. But actually, what I want to talk about is how ultra-diffuse galaxies can be used as stress tests of dark matter physics. And this is work I've been doing at Yale with Peter van Dokkum, but also with a lot of amazing people throughout my PhD that are all listed here, and some of them are here as well. So let me start by talking about what are ultra-diffuse galaxies in a nutshell. So these are galaxies that were rediscovered about a decade ago. And what is most interesting about them is that they have these extremely low surface brightnesses. You can barely see them, but they are very extended. So here is an ultra-diffuse galaxy shown to scale. And this galaxy is extremely large, having an effective radius similar to that of the Andromeda galaxy here. But it's so low surface brightness that it has this luminosity similar to the dwarf elliptical galaxy shown for comparison here. So these are galaxies that are very large, very faint, and very interesting for many reasons that I hope to convince you throughout this talk. So only by looking at this image, we can already start to think on ways these galaxies could be formed. They could have come from dwarf galaxies that have undergone some internal processes that were able to enlarge them. And this could be having very strong stellar feedback or having high spin halos, any process that would be able to puff them up. And this is what we call a puffed up dwarf formation scenario. On the other hand, we think of these more exotic formation scenarios that UDGs could have been born in this very massive dark matter halos, forming a lot of star clusters at the beginning of their lives, but then they quench early on, they don't form enough stars, and they don't become what they were supposed to be. And this is what we call a failed galaxy. So it's a galaxy with a stellar mass of a dwarf trapped within a halo of a more massive galaxy. In terms of observational properties, we know that UDGs span a wide variety of them. They can be in the field or in very deep within clusters. They can have a variety of colors, from being extremely star-forming to very quiescent galaxies. In terms of ellipticities, they can be very elongated or round, but one of the most interesting properties of them is that they can have these extremely weird globular cluster systems, from being completely devoid of them to having hundreds of globular clusters in galaxies with stellar masses of about 10 to the 8. So this is very weird and something that we explore in a lot of details. So throughout my PhD, we have been trying to find the main properties of ultra-diffuse galaxies and how to associate them with these formation scenarios. And this is one of our main results, where we ran a clustering algorithm on all of the properties that we had available for them and tried to understand what are the main classes of UDGs. And we found two of them. The green one here, class A, has all of the properties that are very similar to dwarf galaxies in general. They have very low masses, a normal number of globular clusters, basically properties similar to dwarf galaxies apart from being extended. And this is, we associate galaxies in this class A with having this puffed up dwarf formation scenario. On the other hand, we have these galaxies on class B, which are very weird. They have these very high mass to light ratios, a lot of globular clusters, a lot of mass trapped within the globular cluster systems, very low metallicities, consistent with this early quenching formation scenario. And these galaxies, we associate them with having this failed galaxy formation scenario. So we are now able to understand UDGs statistically and talk about them, really associating them with two main formation scenarios. When we look at the main contributor of the separation of these galaxies between classes, the number of globular clusters really rules the separation, contributing more than 20% of the separation. And then, if we are talking about this and about ultra-diffuse about failed galaxies and all of their weird globular cluster systems, I think it's nice to talk about some of the most weird ones. This is NGC 5846 UDG1 in a work led by Shani Danieli, who's here. And this UDG is so nice because you can clearly see all of the globular clusters on top of it. This galaxy has more than 70 globular clusters. And the main conclusion from this paper is that 13% of the stellar mass of the galaxy is within the globular clusters, and that the galaxy may have once been just globular clusters, and now the stellar mass is made out of disrupted GCs. So this is really interesting to understand UDGs and failed galaxies in more details. Another very interesting galaxy is Dragonfly 44, is a galaxy at the Coma cluster that has now been proven to have more than 80 globular clusters. and has a velocity dispersion of about 40 kilometers per second. Again, for a galaxy of 10 to the 7, 10 to the 8 stellar solar masses, this is extremely high. And the main conclusion from this paper, which is led by Peter van Dokkum, is that this galaxy is so dark matter dominated, even in the centers, that you have an unobstructed view of dark matter when you look at these galaxies and when you study them. Now, you may be thinking, okay, so ultra-diffuse galaxies are galaxies completely dominated by dark matter. Let's study them in more details. But actually, there's another step in the weirdness, because then when studying UDGs, we also found galaxies that are completely devoid of dark matter. And this is a series of works led by the group at Yale, where they found a group hosting more than 10 ultra-diffuse galaxies that have no signs of dark matter within their inner regions. So the main idea of the galaxies formed here are through this bullet dwarf collision, which is a miniature of what happened in the bullet cluster, where you have two galaxies colliding at high redshift. Here you have dark matter in black, gas in green, and stars in red. So when these galaxies collide, if you assume lambda CDM and that dark matter is collisionless, it just passes through, and then in the end you have a trail of newly formed galaxies with a lot of overmassive globular clusters, which are formed by this very high pressure collision. And then you have two dark matter dominated galaxies at the tips of this trail, which are the remnants from the beginning of this collision. This has been recently found for a third galaxy in the NGC 1052 group and led to this beautiful press release by Michael Keim, which is a graduate student at Yale University. And here you can clearly see the separation. So you have dark matter going away, and then all of these dark matter deficient galaxies forming at the tip, at the middle of this trail here. And this is DF9, the galaxy that was shown to be dark matter deficient. This has been recently also confirmed with IGLI simulations, again, forming the same thing: dark matter dominated galaxies at the tips of the trail and dark matter deficient galaxies in the middle. And what is interesting about this simulation is that they predict that there should be 11 of these out of 100, well, every 100 cubic megaparsecs. So we should be able to find more of them and move the discussion away from just one group to be a more widespread class of galaxies. So we've been going after this for a while, and we were able to find now a second trail of dark matter deficient galaxies in the Fornax cluster. These are the two main galaxies. And again, what is interesting here is that we always see these properties combined, galaxies that are dark matter deficient and that have these overluminous globular clusters. So the same collision that is able to separate baryonic and dark matter is also able to create, to change the intercluster mass function, the initial cluster mass function, to form these overmassive globular clusters. So as I said, these galaxies have two main properties. They have this top-heavy globular cluster luminosity function, so they have a lot of overmassive clusters, and they have a small amount of dark matter. And we do this by measuring their velocity dispersions and comparing this with theoretical predictions of what would be the velocity dispersion of galaxies that have no dark matter, so only stars contributing to their dynamics, and galaxies living in normal cuspy dark matter halos. Now, I think in terms of how far we've come, we've done a lot in the past 10 years, but there are a lot of things that I would still like to see in terms of simulations. I think it would be really important to understand the impact of the collisional parameters on the outcomes of these collisions. More even if we try different dark matter models, can we probe the cross-section of dark matter and what comes out of this? And also, how often can collisions of more than 300 kilometers per second can happen in low density environments, which is where we see these galaxies. And then in terms of observations, I think we are now starting to find more of these galaxies throughout the sky and to map them out and to really constrain the formation scenario. But it would be really important also to find the systems while they are forming. And now I would just like to talk very briefly about Gamma 526784, which is probably one of the most beautiful UDGs you'll ever see. It's so nice. And this galaxy caught our attention because we think it could be the progenitor of one of these bullet dwarf galaxies. And this is because it has this red and dead stellar body with a stellar velocity dispersion of about 10 kilometers per second, which is in the ballpark of being dark matter deficient for the stellar mass of the galaxy. But it has this trail of forming star clusters that if they coalesce and become overluminous clusters, then we are exactly where we want to be, galaxies that are dark matter deficient and that have no dark matter, and and that have overluminous clusters. And what is interesting is, again, this galaxy is completely isolated, but it has only this other small galaxy here, which is about 4 Archimedes away. And it's the only galaxy that could have interacted with it and formed all of these clusters. But if this happened, if we have clusters of about 100 mega years that were formed by this galaxy that is 4 Archimedes away, then this collision should have happened at more than 400 kilometers per second. So this is exactly the ballpark of a bullet dwarf collision. So yes, very exciting. People seem to like it as well because we got time on James Webb, we got time on VLA, so we're very excited about this. So keep tuned. And now just to finish up, I think ultra-diffuse galaxies are really important probes of dark matter in general, probing both the extremes of very massive over galaxies dominated by dark matter and galaxies that have no dark matter at all, and the interplay between baryons, globular clusters, dark matter, and everything that is really extreme about these galaxies. So yeah, that's it. Thank you so much.